Good afternoon to all. Welcome to the final week tutorial session of NPTEL course Power Plant Engineering. My name is Ananthakrishnan. I do this problem solving session as part of the PMRF TA duty. We can actually move into the questions. So in this week, we will see a few multiple choice questions and numerical questions based on the economics of power generation and environmental aspects of power generation. And we'll initially deal with these questions, and then the last half an hour we can discuss a bit about the main topics that we had encountered in the previous 7 weeks. I can give you an overview about how to solve a problem on Rankine cycle. Yeah, the question is the load factor of a power station is defined as the maximum demand by average load, load into maximum demand, average average load divided by maximum demand, and none of the above. Answer is right. It's the load factor is defined as the average load to the maximum demand. The ratio of the average load to the maximum demand during a given period is defined as the load factor. You can actually write the load factor as the in terms of the units generated in time t divided by that is actually the load part and the maximum demand. For time t. The load factor will be always less than 1 because the average load will be lower than the maximum demand in all the cases. So it will be less than 1 as the average load will be lower than the maximum demand. Look into the second problem. It's based on the economics part. Annual depreciation cost is calculated by a sinking fund method, straight line method, both A and B, or using an estimate value. So the answer is no D. The answer is option C. Basically, what do you mean by depreciation? Depreciation is actually the gradual loss or decrease in the value of a property. Uh, the first two methods, sinking fund method and straight line method, are the popular methods by which we can estimate the depreciation cost. Straight line method is very straightforward. So you assume that the the value of the asset will be decreasing by the same quantity every year until its end of the life. So that's why you expect the total cost, the total value to be going down in a straight line manner. The value decreases by the same decreases by the same amount every year. The other one is sinking fund method. This is more like the compound interest that we used to study. So here, actually, what happens is the depreciation of the property is assumed to be equal to an annual sinking fund plus the interest on the fund that for that particular year. So this annual sinking fund is termed as the depreciation amount. Annual plus the interest is considered as the depreciation amount. So it can actually estimate it by using a quantity by an equation. So the sinking fund is defined as A is equal to 1 plus R by 1 minus 1 by R by M into P. So here R corresponds to the rate of interest. M corresponds to the number of payments per year. And then N is the number of years. And P is the periodic contribution to the sinking fund. A is the total money accumulated. So this actually can give the amount by which the value will be depreciating over the years. So these two are the normal methods by which we calculate the depreciation cost. Estimate value is not purely technical. So it has to estimate, so it has to take into account the person who estimates it. So the technicality part will not be there. So that's why we go for both A and B. Look into the third problem. Approximate estimation of power demand can be made by the method or methods. Load survey method, mathematical method, economic parameters, all of the above. Yeah, the answer is all of the above. basically the power demand, right? It can be done by, it can be actually determined by three methods. One is survey, and the second one statistics, and the third one mathematical method. The survey method includes the expert's opinion, uh, Delphi method, etc. Statistics takes into consideration econometric method, then trend projection method, and some regression method to calculate the power demand. Can be kind of a forecasting, similar to forecasting that we would see in the IM and OR regression methods. Mathematical methods, time series analysis based on the past data can be one method. So all this can be a useful tools by using which we can calculate the power demand. Looking at the fourth problem. In India, the tariff for charging consumers for the consumption of electricity is based on its freight meter rate, block meter rate, a reverse form of block meter rate, two-part tariff. Yeah, that's kind of right. The question is regarding something else actually. So straight meter rate is very obvious, right? So the tariff would be written as C is equal to uh, PY. So the depending upon how much will be consumed, the charge will be directly proportional to that. That will be straight meter rate. Block meter rate is uh, consists of different intervals. Maybe consider three blocks. So initial block will be having one rate. The next will be having slightly different rate. And the remaining will be at an altogether different rate. And then a reverse form of block meter rate. And two-part tariff. Two-part tariff is actually will the same thing that you have mentioned. It will be having a fixed charge plus the variable, the dynamic running charge. Block meter will be having several intervals. So the first few will be having very high rate, then less rate, then lower rate. A reverse form of block meter tariff, block meter rate will be inverse of this, right? So for the first few units, it will be lower rate and then high and even higher. So which out of the four will be right? So we would have observed, right? It's a reverse form of the block meter rate that we use in India. The initial few units will be having the lower rate, then it keeps on increasing to prevent the consumption. To prevent the overconsumption of electricity, we in India opt for this kind of tariff intervals. So option C is the right answer. Yeah. The question is regarding thermal power plants. These are much preferred because the gestation period is much shorter compared to the other big plants. Minimum pollution to the environment, no water source is required, minimum maintenance cost are lower. We can rule out the last three. Pollution is involved since you have to burn some kind of fossil fuel. Water source is definitely required for condenser as well as in the Rankine cycle. Maintenance costs are low. No, there will be sufficient maintenance process because high pressure, high temperature systems definitely it has to have got sufficiently good maintenance. So the answer is the option A. Its time to yield result will be very short, very much shorter compared to the other big power plants. For the volume or the magnitude of the power it generates, it does that immediately compared to the other thermal power plants once it's a setup. So that's a straightforward question. And we look into a numerical right now based on the demands. And once we solve that, we can actually move into a bit of theory or just revision of a few topics that I have touched upon in the previous few weeks. Look into the problem and try to solve it and also try to solve it. So hope you had an opportunity to look into the question. I'll read through it. The peak load on a 50 megawatt power station is 39 megawatt. It supplies power through four transformers whose connected loads are 17, 12, 9, and 10 megawatt. The maximum demand for these transformers is 15, 10, 8, and 9 megawatt respectively. If the annual load factor is 50% and the plant operates for 65% of the period in a year, based on the given information, find out average load on the power station, energy supplied per year, demand factor, diversity factor, and the power station use factor. So if you haven't solved it, I'll try to solve it. Then we can move into the revision progress. Okay, the first part of the problem that we have to determine is the average load on the station. So before that, we can note down the quantities that are given in the problem. It's mentioned that the power station rated capacity is 50 megawatt. This is the rated capacity. And this is the demand, maximum demand. Then it supplies power through four transformers whose connected loads are 17, 12, 9, 10 megawatt. So the sum of the connected loads will be equal to it will be equal to 17 plus 12 plus 9 plus 10 equal to 48 megawatt. If the annual load factor is 50%, load factor is given as 50%. We have seen in one of the previous problems what is load factor, and the plant operates at 65% uh, for uh, of the period in a year. So that is also given. Then the maximum demand for these transformers are given as 15, 10, 8, 9 megawatt. So some of the maximum demands equal to 15 plus 10 plus 8 plus 9, that is equal to 42 megawatt. Factor equal to 0.5. Uh, the first part of the problem, we have to determine the average load on the power station. Average load on the power station. So how can we determine the average load on the power station? So in one of the previous problem, we have seen load factor. The load factor will be equal to maximum. Uh, it could be defined as the average load divided by the maximum demand. So we know the maximum demand in this particular problem. So and the load factor as well. From there, we can get the average load on the power station. So average load on the power station will be equal to the load factor multiplied by the maximum demand. Yeah, that will be equal to 0.5 into 39 megawatt. That will be equal to 19.5 megawatt. So that will be the average load on the power station. Second part of the problem, we have to determine the energy supplied per year. So how will you determine this? So we have calculated the average load, right? So this average load multiplied by time should give the energy supplied per year. So basically, it is 19.5 megawatt multiplied by time. For an year, it will be everything is annual, right? This is annual load factor. So we have to multiply it by year to get the energy supply per year. So that is 365 into 24. Uh, 365 into 365 days. No, actually, energy supplied per year could actually represent it in terms of some unit, right? So you know the kilowatt hour unit. So I'm trying to write it in terms of kilowatt hour. So time could be written as this many number of hours will be there. Uh, okay, understood. Understood. The plant operates for 65 percentage. Uh, for in this particular problem, we need not take that. So that is not required. So we have to calculate the average load and then multiply it by the time. So there can be a bit of confusion, right? The plant operates for 65 percentage of the period in an year. Yes, there can be a bit of confusion, but we just need to take the 365 days and the 24 hours to get the total energy supply per year. So I understood that you meant to say that this is uh, 65 percentage of the period in an year. But that doesn't actually, this can be slightly confusing the way it has been put. Uh, the plant operates for 65% of the period in a year. But then again, this load that we have, right, 19.5 megawatt, uh, this should take into account the this 19.5 megawatt that is for a single day, right? So for a single hour. So that should take into account the period in which the plant doesn't work as well. So that's I understand that this is tricky and slightly confusing, but the solution that I'm having, I have prepared. I have looked into some textbooks and found out that this is the time is actually taken as 365 into 24. I can correct it if the equation is something else. For the time being, just keep this as it is. Uh, the average load multiplied by the time can be it can give the energy supply per year. This is actually a redundant information in this problem, the planned operate and the planned operation time. So just ignoring that 65% of the period in a year, you'll get the energy supply per year. We have to determine the demand factor, diversity factor, and the power station use factor. So you are doubt of that 65%, right? So where will that be using in the whole problem? That will be used in certain cases, in certain areas. And I'll show where it will be used. So the demand factor is defined as the maximum demand to the sum of connected loads. Maximum demand is given as 39,000 kilowatt. The sum of connected loads will be, in this particular problem, it's equal to 48,000 kilowatt. So the answer is 0.8125. The diversity factor, it's something similar, but it has the sum of maximum demands on the top to the maximum demand that the plant encounters. So that will be equal to 42,000. That is a maximum demand that we have calculated in the previous part of the problem. So this is 42,000. Divided by, this is 39,000. So the answer is 1.077. And the final part of the problem, we have to determine the power station use factor. So this is equal to, the use factor is defined as the energy generated per year, use factor, energy generated per year divided by the rated capacity multiplied by the number of operating hours. So the energy generated per hour you have calculated in the first part of the problem. In the second part of the problem, energy supplied per year. So that is 170.82 Newton power 6. The rated capacity is 50,000 kilowatt, and the total number of hours per year 8,760 multiplied by the operation factor, operation time, that is 65%. It's 0.65. So this will give answer is 0.6. So that's where the power station use factor comes into picture. So basically in this problem, we have calculated the average load on the power station, energy supplied, average load multiplied by the time, then demand factor. The diversity factor is straightforward. The maximum demands, some of the maximum demands divided by the maximum demand. Demand factor is basically maximum demand divided by the sum of the connected loads. And then power station use factor is the energy produced by the power station divided by the maximum energy that it can produce based on the rated capacity. Uh, so if annual load factor is given as 50%, so based on that, we have determined this one, this one. The power station, based on its rated capacity, can work for only just 5694 hours. That's where the plant operates for 65% time comes into picture. So if that is capable enough of producing this much energy, that will determine the use factor. If the entire amount is used, then the use factor will be 1. If not, you have to determine how much is the use factor. In this case, it's 0.6. look into this problem. It's based on a Rankine regenerative cycle with an open feed water heater. Uh, so I'll read through the problem. A regenerative Rankine cycle with one open feed water heater is considered to produce 1 megawatt of power. Steam leaves the boiler and enters the turbine as superheated at 4 megapascal pressure and 360 degrees Celsius temperature. Assume the feed water heater pressure as 2 megapascal and condenser pressure as 30 kilopascal. The turbine and pump efficiencies as 90 and 85% respectively. Perform the first law thermodynamic analysis to determine net boiler heat transfer, net heat rejected in the condenser, and the thermal efficiency of the power cycle. I'll draw the schematic. So there is this boiler, and then it goes into the turbine. And a portion of that will go into the condenser, and there is this feed water that will be drained out of the turbine. So I'll show that where it was used. Then it goes into the turbine. It goes into the pump. And then goes into a feed water heater, which takes in the water, which is the steam, which is bled from the turbine to preheat. And then it goes into the another set of feed water pump to the boiler. So if I denote after the boiler, it will be 1, then this particular point can be 2, this is 3, condenser exit will be 4, pump exit will be 5, exit of the feed water 6, and this particular point 7. So once we have denoted all these points, then we can denote them in the ES diagram where exactly it is, where exactly it will appear. And using the standard properties, we can determine, uh, we can actually calculate the quantities just like that. So in certain cases, the values might not be reasonable, but we can actually uh, compare between the values that we get in this case to the usual expected efficiencies in certain cases. So this is don't take the values that we get from these equations. Don't take it seriously. This is just the way a problem can be solved of the ranking cycle. Uh, there is the realistic nature of the values can be compromised in this problem. It just look in the way the problem is solved. That is more important. So in this particular problem, the power output is given as 1 megawatt. Then the inlet pressure to the turbine uh, the P1 point is written as 4 megapascal. Inlet temperature to the turbine T1 point could be written as 360 degrees Celsius. Then pressure, feed water pressure is given as 2 megapascal. Pressure of feed water heater could be written as P2 equal to 2 megapascal. Pressure in the condenser equal to 20 kilopascal. Turbine efficiency is 90%, and then pump efficiency is 85%. The first part of the problem, we have to determine the net boiler heat transfer. So the net boiler heat transfer takes into account point 1 and 7. Uh, the point 1, we know the temperature, we know the pressure, and if you try to plot them on a TS diagram, you'll see that it will be in the supersaturated region. Sorry, it will be the superheated region. And we do not know anything about point 0.7. So we can't calculate anything until and unless we identify the corresponding properties at the state points and then solve it. So on a TS diagram, on a TS plane, it could be drawn as, so the point 1, this will be the point 1, and then there will be if this would have been a straight line, if the whole process would have been isentropic, but it's not. That's why it will shift towards the right in second in this case. And then condensation, then the pump, feed water heater, the cooling pump, and then there is the bleeding that happens somewhere here. So this point, a portion of the water, the portion of the steam will be released for the feed water heater at 2 megapascal. And then the pressure of the condenser, the third point will be, this pressure will be 20 kilopascal. So this particular point will be 4, 3, 4, 5 mixed with 2, and we will get the 0.6, 2, and it comes out 7, 1, 2, 3. Yeah. This pressure will be 2 megapascal, and this pressure will be 4 megapascal. This gives the total the whole Rankine cycle with the regenerative feed water heater on a TS plane. We need to seek the help of a steam table or where a steam table it can give the properties of water in the saturated state as well as in the superheated regions and also in the subcooled region in certain cases. So so I'll give the data in this case and we can try to solve it. So the point 4 will be at point 4. It will be saturated liquid, saturated water. So the enthalpy will be equal to enthalpy of the fluid at the pressure 20 kilopascal. Its value will be equal to 0.4684 into kilojoule per kg. Then similarly at this particular point, we can calculate the specific volume. At the point 4, its specific volume nu will be equal to specific volume of saturated liquid at this same condition. It will be equal to 1.1871 cube per kg. So we know both these points. The So the way in which normally we calculate the enthalpy of the sorry, the work done in the pump will be in terms of the specific volume at the point 4 multiplied by the pressure difference between 0.5 and the point 4. So that will give the work done in the pump. So we know the value of nu, and since it is water, we do not expect the specific volume to change much during the pressure pumping process. So the specific volume we can take to be the same. We multiply it by the pressure difference will give the work done in the process. The difference in work, specific work will be equal to the specific change in the enthalpy in the process. From that, we can get the enthalpy of state 0.5. That is one way that we can calculate the 0.5 enthalpy. So this is 0.4. Now we move to the other extreme, that is 0.1 before the turbine. So its temperature and the pressure we know, that is 4 megapascal and 360 degrees Celsius. It's a superheated region corresponding to at 0.1. At 360 degrees Celsius and 4 megapascal. The enthalpy H1 could be written as 3358.8 kilojoule per kg. So this is from the steam table. So once this is done, then we can calculate the similarly from the steam table, we can determine nu1 that will be equal to 0.1049 meter cube per kg. Now we how to move to state point two, how to determine the enthalpy at state point two. So for that, we have to make use of the entropy at the state point one. And in ideal case, the entropy at the state point two should be same as that of the entropy at state point one. But since there is an isentropic efficiency of the turbine given, we can't take that. We should actually determine the so in this particular case, we can using the entropy at that particular say at the point one to be same as point two, and pressure at point one and two to be different, right? In this case, the second point pressure is given as 2 megapascal, so corresponding to 2 megapascal, and the entropy at point one, we can get a new enthalpy. That new enthalpy, we have to now we have to make use of the turbine efficiency of 90% to determine the new state point. Once you get the new state point, so that particular point enthalpy we can calculate using the using this efficiency of 90%. So that's how we can calculate the point two's enthalpy. On point three, similarly, this 90% efficiency is there. We have to determine that. So point we know the point one, and we have to calculate the other properties. Just give me a moment and let me cross verify the value of point two, and then I'll follow it from there. I beg your pardon, there was a small correction in the values. I, I made a mistake in the values. So these are not the same. So I had the saturated liquid value at 20 kilopascal, that's value will be equal to 251.4 kilojoule per kilogram. Uh, so that is something that we have to use. And then at 360 degrees Celsius and 4 megapascal, H1 will be equal to 3117.5 kilojoule per kilogram. And then new one, we do not require new one in this case. We require the entropy S1. So the S1 at that particular point will be equal to, from the steam table, will be equal to 6.627 kilojoule per kg Kelvin. This is point 1, that is the superheated region. And the second part, the feed water is taken from a condition 2, that is a superheated region. So we need to identify the point 2. At point 2, S2 should be equal to S1. Uh, so that is equal to 6.6217. We can actually check for the authenticity of the condition that we have. So we at 2 megapascal, the saturated gas entropy will be equal to 6.33. Since S2 is greater than ST, so we can say that it's comfortably in the superheated region. So once we know that, we have to actually determine the new the new enthalpy at the point 2. So corresponding to this S2 and the pressure of 2 megapascal, we get H2 is equal to 2943.9 kilojoule per kg. But this is the we have considered an isentropic process, but there is an isentropic efficiency that is given this problem, that is 90% for the turbine. So efficiency turbine will be equal to 90%. That will be equal to the H2 dash mu H2 minus H2 divided by H2. This one will be so this is a turbine work producing device. So the isentropic efficiency will be equal to the work produced, the actual work produced to the isentropic work produced. The isentropic work produced will be equal to H1 minus H2 dash. Sorry, H1 minus H2. This process and to the actual work will be H2 dash. So H2 dash will be the H2 dash will be the actual work produced. So from here we can determine the value of H2 dash. Other quantities are known. This will be H2 dash will be equal to 2273.61 kilojoule per kg. So this is the actual value. So this will be equal to 2 dash. Ideal process will be coming right here, 2 dash. Once we get to see H2 dash, so we got the actual enthalpy at the point 2. Then coming at the exit of the turbine, the actual exit of the turbine, the pressure P3 will be equal to 20 kilopascal. Similar to the previous case. The S3 should be equal to S2. So we have to actually determine the entropy, the actual entropy of the state point, uh, the state point here. At the we can assume that the entropy at this particular point won't be varying that much, and therefore using the entropy, actual entropy at the state point 1, we can determine the enthalpy at the state point 3 as well. So here S3 could be written as S2. So that is the ideal case 6.6217. Then since only a single turbine is said, since there are no two turbines, we can take S3 equal to S2 equal to 6.6217, the same quantity. So once we know the entropy, we can actually determine the dryness fraction at the point 3. So S3 will be equal to SF plus X3 into SFG corresponding to 20 kilopascal. So this quantity is 0.832 and this quantity is 7.075. So once we get to see that, then the value of X3 will be equal to 0.818. Once we know this value, 0.818, we get to see that this is the dryness fraction at the point 3. This is based on the entropy value of S3. But then we in this particular problem we have to calculate the actual value of enthalpy at the particular state point. We know the efficiency 0.9. That will be equal to the same as in the previous case, H1 minus H3 dash divided by H1 minus H3. So from here we'll get the value of H3 H3 dash. For that we require H3. So since we know the value of S3, we can, and using this value of H3, we can calculate H3. H3 is equal to HF plus H3 of HFG. So that will give at 20 kilopascal, the value of H3 will be equal to 2179.85 kilojoule per kg. This is the ideal value, right? So then we have to substitute that H3 here to calculate H3 dash. So H3 dash will be equal to 2273.6 kilojoule per kg. So this is the value of S3. So we go to see that, yeah, we have to make sure that this is not the actual exit of the turbine. This is ideal, based on the ideal turbine exit, based on the same entropy as that of the inlet to the turbine. So we get to see H3 dash is equal to this one. Now we have to move to the other side. We know that the uh, point 4 pressure will be equal to 20 kilopascal. Therefore, H4 will be equal to HF will be equal to 251 point 251.4 kilojoule per kilogram. Then what we can try to do is that we can calculate the enthalpy at we can try to calculate the enthalpy at the exit of the pump using the pump efficiency which is given. So the in the pump efficiency the uh, is given as 85%. At 0.5, this is the pump efficiency. This is a work input device, so the actual work input will be higher than that of the uh, isentropic work. It's reverse of the turbine. So here in this case, we know the value of H4. We need to calculate the H5 uh, based on the specific volume at this particular point, at the particular point, that is point 001 017 meter per kg. So the basically for an ideal case, for an ideal pump, V into delta P, the specific volume in delta P will be equal to H5 minus H4, H5 minus H4. So from here we can calculate the value of H5. So H5 will be at 2 megapascal. So this the difference will be equal to H5 will be equal to H4 will be 251.42 plus 0.001017 into in terms of this is kilojoule per kilogram, right? So 2 megapascal could be written as 2000 minus 20. So that will be equal to 253.43 kilojoule per kg. So this is the ideal value. So there is a pump efficiency in this case. So pump efficiency will be giving the work ideal to the work actual for a work input device. So work ideal will be equal to uh, work ideal will be equal to H5 minus H4 divided by H5 dash minus H4. From here we can calculate H5 dash is equal to 253.7. Not a huge change. So this value will be equal to 0.85. So for now, this is 0.5, and then there is a turbine, and it mixes together in the feed water and produces produces water at 0.6. So the pressure at 0.6 will be equal to same as that of 2 megapascal. Then we have to calculate the enthalpy at the 0.6. That will be equal to the fluid enthalpy, saturated fluid enthalpy at 0.6 at 2 megapascal. So that can give an idea of say 0.6 at 6. At 6 will be equal to HF at 2 megapascal. that will be equal to 908.47 kilojoule per kg. Then at 0.7, at 7, that is after the pump. So at 0.6, we should also calculate the new. So that is equal to 0.001 1177 meter cube per kg. So we go to see H6 and HF. Now, just like the previous case 4 and 5, we have to determine, just like the previous case 4 and 5, we have to determine 7 as well. H7 minus of H6 will be equal to the ideal enthalpy at the exit of the high pressure pump will be equal to mu at 0.6 into delta P. From here, H7 will be equal to 908.43 plus mu will be 0.001177. Just like the previous case, 4000 minus 2000, that will be equal to 910.8. This is the ideal value. Now we have to determine the actual value. How? Just like the previous case, pump efficiency will be equal to 0.85 will be equal to the work done ideal minus work done actual. So that will be equal to H7 minus H6 divided by H7 dash minus H6. So the actual enthalpy H7 dash will be equal to 911.23 kilojoule per kg. So that completes the enthalpies of all the state points starting from 1 to 7. Now we need to determine the net boiler heat transfer, the rate of heat rejected, and the thermal efficiency of the power cycle. So since this is a regenerative cycle, we need to determine how much amount of water will be bled from 0.2 to 0.6. For that, we need to go for the mixing that will happen from 0.2 in between 0.2 and 0.5 to give the 0.6. So that is a mass balance in this case. How that will be considered? We assume that a fraction of the, if 1 is the quantity, if 1 kg per second is the flow rate that happens in the turbine, fraction of that y will go to the feed water, and the rest 1 minus y will go to the low pressure pump. So 1 minus y or water and y feed water will mix together to form again 1 here. So 1 kg per second. This is 1 minus 5 kg per second. Kg per second. This is 1 kg per second. Okay, so we go for the fraction of this steam extracted. So here the in the feed water heater mixer, what we could expect is that by H2 dash plus 1 minus 5 of H5 dash will give H6. We know the value of H6, H5, and H5 dash. We solve for y, that will be equal to y is equal to H6 minus H5 dash by H2 dash minus H5 dash. So the values we substitute straight away divided by 243.7 is the fraction is 0.241. So we get to see the fraction of the steam itself. So the value of Y will be 0.24. 24% of the total feed, total water will be fed through to the mixer. So now the main part of the problem, we have to determine the net boiler heat transfer and heat dissipation in the condenser and the thermal efficiency of the power cycle. For calculating all this, we require the network into the cycle. So the network is the positive work minus negative work, the turbine work minus the pump work. Since the quantity of the turbine has to undergo, since the bleeding takes place in between the turbine expansion process, the actual work input will be having two parts. One is the one before bleeding, the other after bleeding. Similarly, the pump will not be having the same mass flow rate. The pumps will not be having the same mass flow rate. The lower pressure pump will be operating at a operating with a lower flow rate because that is 1 minus 5, and the higher pump will be having a higher flow rate, that is 1. Uh, so using that, we have to determine the turbine work per kg. So the turbine work could be written as so the h1 minus h2 dash multiplied by 1 plus 1 minus 5 into h2 dash minus h3 dash. So just substitute the values of h1 and h2 dash, h2 dash, h3 dash, and y will get the value of 677.653 kilojoule per kg. Similarly, the pump work will be equal to 1 minus y into h5 dash minus h4. That is the lower pump plus x7 dash minus x6. So that is equal to h. So the turbine work is done, pump work is done. The mass flow rate and dot will be equal to, in this particular problem, it's mentioned. The what feed water heater it produces as Rankine cycle produce 1 megawatt. So that will be equal to 1000 kilowatt. So you can write it as 1000 kilowatt divided by the network. So the network will be equal to turbine minus pump work. That will be equal to 673.103 kilojoule per kg. This will be equal to so this is kilojoule per kg. So this will give the value of the mass flow rate. That now we have to calculate the heat transfer to the boiler to in. That will be equal to h1 minus h7 dash. So that will be 2206.31 kilojoule per kcal. So this is specific heat, right? So the rate of heat transfer. So rate of heat transfer in terms of kilowatt is equal to this quantity 2206.31 into mass flow rate of 1.485. So the value will be equal to 3276.37 kilowatt. So this is for the rate of heat transfer to the in the boiler, the net boiler heat transfers. So that is equal to 3276.37 kilowatt. A. And then similarly, we can calculate the rate of heat rejected. That will be equal to m dot into h3 dash minus h4. So we have to remember that in this problem we didn't calculate the actual dryness fraction. We just made use of the straight line isentropy process. We calculate the dryness fraction if the whole process would have been isentropic, and from there we calculated the entropy at this point. So entropy will be is the same. Using that entropy, we have calculated the dryness fraction, and from that we have calculated the enthalpy at this particular point 3. So the actual point will be 3 dash. That is based on the isentropic efficiency of the turbine. So we have calculated the actual enthalpy at this point. We did not calculate the dryness fraction at this point. It was not required in this problem. Unless asked, we need not measure that. Rate of heat rejected, yeah. So just like the previous case, we have to multiply it by the enthalpy differences. So we get to be 3002.9. The thermal efficiency will be equal to this minus this 3276. So the work net by Q input. So the work net will be 673.103 kilojoule per kilogram, not kilowatt. And similarly, the heat input in terms of kilojoule per kilogram without considering the mass flow rate. So that will be equal to 2206.31. The efficiency will be equal to 30.508%. Do not take these values seriously. This is to give a flavor of how to solve the problems of Rankine cycle. So here we have gone step by step for a regenerative water cycle, Rankine cycle. We have identified all the the properties of making enthalpy, entropy at all the state points. And in these problems, there were certain cases where the enthalpy, the isentropic efficiencies of pump as well as the turbine has to be considered. So we have also made sure that we have considered all that to get the new enthalpy points. And finally, once we know enthalpies, we have to go for the mixing in the feed water between the feed water as well as the pressure the pumped water. So these two will be giving the amount of steam blend from the feed water, and then using that fraction, we can determine the actual work output, the work output in the turbine and the work input required in the pump and the net work. And once we know the enthalpies, we can calculate the work, the heat input into the boiler and the heat rejection in the condenser, and based on that, we can calculate the efficiency of the Rankine cycle to be around 30.5. So that was one problem that I wanted to discuss that I could discuss initially. That takes into account the isotopic efficiencies of both the things and to couple along with the regenerative cycle. So this was based on the I guess third week lecture, second or third week lecture that I couldn't discuss at that time. So apart from that, we have seen in this week a few numericals and multiple choice questions based on the economics part. We couldn't see much regarding the other sections. So if you have any doubt, you can actually post them in the course forum, and the TAs will attend those. So all the best for the exam, and we can wind it up
Sir?
right now.
हेलो सर
हेलो.
सर एक क्वेश्चन था मैं पूछ सकता हूँ
हाँ, यस.
मैं बोल रहा था हमारा जो एनपीटीएल एग्जाम होगा उसके लिए क्या क्या पढ़ना पड़ेगा
NPTEL एग्जाम के लिए.
हाँ हाँ
So you have to follow the lectures and the weekly assignments. So that will be more than enough. The syllabus you already would have, right? So have you
yes
logged into the course website and seen the lectures? Hello.
हाँ हाँ
So you would have seen the course website, right?
yes
So on the left hand side, there will be tabs. In every tab, there will be lectures, video lectures available. You have to look into those video lectures,
yes
and you would have already seen you would have already solved quite a lot of assignment problems, right? So the final exam will also follow a similar pattern.
okay sir
Okay, then we can wind it up. Thanks for attending these tutorial sessions. If you have any questions, you can post in the forum. Thank you.